Hello everybody, welcome to your last video lesson before March break. I am going to apologize in advance. I'm running a little bit behind today and I gotta go pick up my kids from daycare. So I'm gonna end up going through this relatively quickly, but remember you can always adjust the speed on YouTube and play it at your own pace, pause it wherever you want. And this stuff today is really not too bad. So we're gonna be graphing cubics. We're gonna learn or go over at least describing the transformations of graphs of cubics and quartics, so things that are to the power of 3 and to the power of 4. So we're going to start off with the parent graphs. Cubic we've already done. Quartic we have not done yet. X, Y. Start off with our parent function or parent points. So f of x equals x cubed, negative 2 cubed, negative 8. Negative 1 cubed, negative 1, 0 cubed, 0, 1 cubed, 1, 2 cubed, 8. And away you go with your points. 0, 0, 1, 1, 2, 8, negative 1, negative 1, negative 2, negative 8. And there's our x cubed. Now we'll do the same thing for our quartic. F of x equals x to the power of 4. Negative 2 to the power of 4 is 16. Negative 1 to the power of 4 is just 1. 0 cubed is 0. 1 to the power of 4 is 1. And then 2 to the power of 4 is 16. So that doesn't really fit on the graph as I have it right now. That's okay. But 0, 0, 1, 1, negative 1, 1. And then 2, 16 would be like really high up. So we'll just make it look kind of a bit skinnier. And same thing there. And there's our x to the power 4 graph. Example 1, describe the transformations that must be applied to this. You did this in grade 11. We did this earlier for our first unit. Now we're just going to specify it with quartics and cubics. So first thing that you encounter is that negative. That means reflected in the x-axis. The next thing we're talking about is the 5. That's like your a value, vertically stretched by a factor of 5. Next thing we encounter is this, which we know moves our graph right 4. So we'll say translated, or you could say shifted right by 4. And the last thing, positive 2. That's like your C value, up and down, translated up by 2. Our next example, 1b, we're going to take that exact same equation and we are going to graph the transform function by mapping 3 parent points through the transformations. So identify that it is a quartic, and our parent points. First thing, so we want to do our transformation notation. So our txy. So we are going to have x plus 4, negative 5y plus 2. And then our parent points, we just did them. Now I know in the question we only said 3. That's because I'm going to do all 5, but you only really have to graph 3 of them unless you really want to graph all 5, because the points are going to end up being, or could end up being, really, really high or really, really low depending. So negative 2, 16, negative 1, 1, 0, 0, 1, 1, and 2, 16. And we're going to put those through all the transformations. x plus 4. So negative 2 plus 4 gives us 2. Negative 5 times 16 is negative 80. Negative 80 plus 2 ends up being negative 78. So already you can kind of see our values are pretty low in this case. Next one, negative 1 plus 4 is 3. 1 times negative 5 plus 2, negative 3. 0, 0 is going to give you 4 and 2. 1, 1 is going to give us 5 and negative 3 again. And 2, so it's going to give us 2 plus 4 is 6. And negative 5 times 16 is negative 80. Negative 80 plus 2, negative 78. And we have our 5 transform parent points. And if you really wanted to make a graph with all of them, you can. But really, I get the idea if I see that, and then you just end up graphing those 3 points. And like I've mentioned before in the first unit, we don't have to, for the homework questions and stuff, I mean, practice the graphing a little bit, but I would assume most of you, once you get to all the ordered pairs, you know how to plot an X and a Y. So I'm not going to bother doing it for here. Once we've done the transformation stuff, we're all good. Our next example, describe the transformations that must be applied to this cubic. First thing you have to do is realize you have a number out front of x. So whenever we have that, we have to common factor it out first. So negative 8. And now we're going to have a square bracket because we're going to have brackets and brackets. And if I common factor out an x, I'm left with x and then plus 2. Cube minus 3. Now we're ready for our description. The negative means reflected in the x-axis. This right here is like our k value. Remember, it's always opposite for x. So instead of dividing by a half, it's like multiplying by 2. So we're going to say horizontally stretched by 2. The next thing we hit, the positive 2. Meant to use purple. Positive 2, which means shifted or translated left 2. And then we have our minus 3, translated down 3. And there's all of our transformations described. The cheater's method. So this is kind of like looking at vertex form. And I'm going to say kind of because it's not really, you're not going to necessarily find this in your textbook. This is just me building on patterns and kind of showing you patterns and ways to think of it if you don't like the transformation notation, or at least if you want a different way to kind of validate what you're doing transformation-wise. So we know a quartic. A quartic basically looks like a quadratic. And you kind of can think of it like having a vertex. So if we want to do it like, or think of the question as like having a vertex, you would tell me that it's 4, 2. So if you had to plot that vertex, you would put it at 4, 2. And if we're drawing parallels to our quadratic function, normally you would use like the step pattern, which if you remember going back to grade 10 and grade 11, step pattern is normally 1, 3, 5. However, for a quartic, so if we go back to our kind of parent function, that was 0, 0, and then we had negative 1, 1, 1, 1, and we had 2, 16, and negative 2, 16. So if you wanted to come up with your own kind of step pattern for this, we started the vertex, over 1, up 1, over 1, up 15, and over 1, up 1, over 1, up 15. So if you wanted to, and again, this is where the numbers kind of get crazy with the quartic, but if you wanted to think of it that way, we could plot our vertex, which is 4, 2. We know that our step pattern is actually 1 and 15. Multiply by your a value, so times negative 5 times negative 5, which would give you negative 5 and negative 75. So once you plotted your vertex at 4, 2, over 1, down 5, over 1, down 5 on both sides, and then from there, over 1, down 75 on both sides. So that's kind of like a cheater's method or a different way to think about it for doing quartics. For cubics, you can think of it as a very, very similar way to that. So we know that there's an inflection point at 0, 0. So if we kind of just for a second do our normal cubic, we know there's an inflection point. That's the point that kind of matters, 0, 0. And then the next point is 1, 1, 2, 8, negative 1, negative 1, and negative 2, negative 8. So I'm going to say step 1 is like stating a vertex. I'm going to write V for vertex, but really the vertex is this inflection point right here in the middle. That's like the start of your graph, the center of your graph. And then you go over 1, up 1, over 1, up 7, and same idea here. Over 1, down 1, over 1, down 7. So it's kind of like having a step pattern. And I'll say the vertex is kind of like our inflection point. And then your step pattern is usually 1 and 7. And you would multiply by your a value. If we look at the equation that I just gave you, it doesn't necessarily look as nice in vertex form, quote unquote, as our quartic. Why? Because there's a value out front of the x. So you have to get rid of that. And how you get rid of that is like this. If I want to move, so we've already factored out that 1/2 before. So 1/2 x plus 2 all cubed minus 3. If I want to bring this 1/2 outside, if I leave that barrier, I have to cube it. What is 1/2 cubed? 1/8. And then you're left with x plus 2 cubed and then minus 3. And the awesome thing that happens there is that negative 8 times an eighth gives you negative 1. So if I wanted to do like, think of it as like an inflection point, vertex, whatever term you want to use there, really it would be negative 2, negative 3. And then our step pattern would be 1 times negative 1 is negative 1, and 7 times negative 1 is negative 7. So you would plot your inflection point, negative 2, negative 3, and then just go up and down 1, up and down 7 on both sides. So it's just another way to think about it if you don't want to do transformation notation. Example number 3, find the x-intercepts. If we are finding the x-intercepts, what do we know y is, or what do we know f of x is? It's 0. So 0 equals 3x plus 6 to the power 4 minus 48. Step number 1, bring the negative 48 over, becomes positive 48. Divide both sides by 3. 48 divided by 3, 16. And at this point, we would have, if we draw patterns to quadratics, you would have had a squared. We have it to the power of 4. What undoes a squared? Square rooting. What undoes putting something to the power of 4? Taking the 4th root. And just like when you do the square root, if it's an even root or an even exponent, you need to do plus or minus. The 4th root of 16 is 2, so we're going to have plus or minus 2 equals x plus 6. Plus or minus 2 minus 6 equals x. At this point, split it off into your two possible solutions. So negative 2 minus 6 equals x, negative 8 equals x. And our other solution would be 2 minus 6 equals x, negative 4 equals x. And there's our two x-intercepts, or two roots, or two zeros. Our last example. Find the equation of the function in the graph, assuming f of x equals x cubed as the parent function. So if you're looking at that, yes, it has the general shape of the cubic. If we want to kind of use the cheater's method, if you want, you would take a look at it. We're looking at our inflection point. So we know f of x equals, don't know my a value, x minus 2 cubed minus 3. If we wanted to use the cheater's method, we'd be looking. So now I have to go over 1. So graphically, it goes over 1. And in this case, it goes from negative 3 to negative 1. So that's a jump of 2. Just double check to make sure it does the same thing on either side. Over 1, and it goes from negative 3 to negative 5. That also is a jump of 2. To determine if it is a positive 2 or a negative 2, look at the end behaviors. Odd function, my end behaviors, as x goes to infinity, y goes to infinity, and as x goes to negative infinity, y goes to infinity, which tells you that it is a positive leading coefficient, so a positive 2. Now let's say, for instance, it didn't go through, or it wasn't really visible that step pattern. You'd have to do this algebraically. And really, we should have done it algebraically anyway, but to show you just in case on like a test or homework question, if it doesn't appear to have like a super nice step pattern, then we're going to do it algebraically. So f of x equals, still use your inflection point, that 2, negative 3. And sub one of the points in. Very, very important. You can just like you can never sub the vertex into vertex form, you can never sub the inflection point into our cubic. So pick one of your other 2 points. Let's say we pick this one, 3, negative 1. Negative 1 goes in for that. 3 goes in for x. Negative 1 minus 3. So when that negative 3 comes to the side, it becomes positive 3. So that turns into 2. 3 minus 2 is 1. 1 squared is 1. So you're left with 2 equals a. We got the exact same function when we used the quote-unquote cheater's method. For your test, you probably should use the algebraic way and then use the cheater's method to just confirm that you did it correctly. Also, sorry, forgot to mention, shout out to Josiah if this sounded really, really good. If this didn't sound really good, then no shout out to Josiah.